Hey, what's up, guys? Yeah. So I have been long time never publish a new video, but I think now maybe I should start publishing something because I recently find that there are still many interesting things that I recently learned. So I think I need to share with you guys, and I hope you guys subscribe to my channel. Okay, so I will spend like 2 videos talking about something interesting. So I will talk about basically the golden Thomas inequality. Okay, but in this video, I will just quickly say what it is, and we prove something very similar, but basically it's very simple. I will prove that something will prove another equality, but basically very easy, but related to it. Okay, so settings basically let's focus on ABR basically Hermitian matrices. So a n by n Hermitian matrices with real coefficient. So basically you can say that ABR basically symmetrized. Okay. And okay, maybe in this case a complex is fine. Okay. And okay, so basically let's say when ABR real, let's focus on when ABR particularly real n by n matrices. So this golden Thomas inequality says that the trace of exponential a plus b, right, is less or equal to exponential a times exponential b and take trace. Okay, so this looks simple, but actually the proof is somehow non-trivial, very non-trivial, and not easy to see why this is true. Okay, so exponential a basically is the matrix exponential, right? So you just sum over a to k factorial k from 0 to infinity. Okay, and hopefully everything is well defined here. And now right, so this is what we're gonna to prove in next video. So this will takes more time. Okay, but we can prove a very simple one, right? So there's another fact which is I will prove today. Basically, is if you take determinant of exponential a and exponential b, this will say as determinant of exponential a plus b. Okay, so notice that since A, B are matrices, right? So they don't commute. So obviously that we definitely don't have this kind of thing. Okay, so this also a little bit non-trivial. The proof. Right? So proof using the Baker-Campbell-Hausdorff, right? So we can write exponential a plus b equals to exponential a times exponential b, and then there's a negative half a and b commutator. So this is Baker-Campbell-Hausdorff, which is non-trivial. Now, so we can take the determinant from both sides. So we get determinant of exponential a plus b, the same as determinant of exponential a times exponential b, and then times determinant of this. Okay, so obviously that this tell you this is true. So the only thing you need to show is basically this guy is 1. Okay, and all you need to do is using the following, right? So given any matrices, exponential x, and then you take a determinant, then this will be just exponential trace x. Okay. So this is easy to prove. So I will prove in a few minutes. But basically, once you have this, then you can show then this guy will be just exponential trace of AB. Half. Okay, so now this is 0, right? Because AB are commutator. Okay. So we prove these results. Okay, so now the remaining thing just very simple, right? You can prove that exponential x for any matrices, if you take determinants, will be the exponential traces. Okay, so easy to prove this because any matrices, right, can be triangular, can be upper triangularizable, right? So basically, there is a basis such that you can change your basis, and x will be upper triangular. Okay, maybe you can use a Jordan form, but that's using the upper triangular will be enough. So basically, there's a matrices P, such as invertible. So P inverse AP. Okay, and A is upper triangular. So upper triangular. So basically, this means that A is basically n by n matrices, and there's only here. All these are have been non-zero, but these are all zero. I'm going to just write, and obviously that determinant of exponential x, right? Simple formula will tell you that this is determinant of P inverse exponential AP, which is the determinant of exponential A. Okay, because right, because determinant is, yeah, these two can cancel, right? Okay, so now you're doing exponential A, right? And okay, so what's this kind of thing, right? So it's obviously that, let's say if your A is like something like this, right? It's basically, let's say maybe it's A1, A2 up to AN, whatever, right? And these are all zero, and these are all something. If you A squared, right? If you do it A squared, you will get A1 squared, A2 squared, AN squared, and these guys are something, and these are all zero. So if you go any power k, this will be A1 to k, A2 to k, AN to k. Right, so if you take a determinant of the upper triangular matrices, will just be the product of all the matrices. Right, so this is easy to show that this is easy, just exponential of all the diagonal matrices. Right, so it's a product of let's say I from 1 to n, and the exponential of all the diagonal matrices. So the matrix element, let's call it lambda I. Basically, this is exponential of sum over lambda I from 1 to n. Basically, by definition, which is a trace of exponential to a trace of the matrices A. Okay, but exponential trace of A is the same as trace of X, right? Because trace of ABC, trace is cyclic, right? Trace AB equals trace BA, right? So basically, it's basically exponential of trace of X. Okay. So this one give you this one. Okay, so that's it. So basically, we prove that this is holds. Okay, so next video that we will spend maybe 30 minutes or however 25 minutes to prove this very interesting inequality. Okay, see you guys next videos. Oh.